Okay, so good day. So for example, we have this beam loaded as shown. So EI is constant and no support settlement. So for example, we are required to compute for the moment at B using the slope deflection method. So some of the parameters to be used for the slope deflection method, we are to consider displacements, rotation, and fixed end moments. Okay. So we have, first to imagine if there is a rotation, we may draw the elastic curve of the beam. So for example, this is the deflected form of the beam. So obviously we'll be having, we'll be having a rotation at point A. So there is a value for rotation at A since there is a hinge support. But since for this problem, no support settlement, we may assume that delta at A is equal to 0. Then, possible that we'll be having a rotation at B since there is a roller support. So we have the value of theta of B, but we don't have a displacement or settlement at point B. Then we have, this is the rotation at C. So we have theta C. But again, the support settlement at C. So for these cases, if we have delta is equal to 0, we have the rotation of the chord member psi is basically equal to delta over L. So which means if this all value, if we don't have support settlements or displacement, we may assume the value of psi to be 0. So how about the fixed end moments? Okay, so we are to separate the span, then compute for the fixed end moments. So for example, span AB, so we isolate the span AB, then assume both ends to be fixed supports. So what is the equivalent fixed end moment for this case? The fixed end moment is equal to the uniform load, the length squared divided by 12. So if you are to compute for that value, FEM is equal to, the uniform load is 40, the length is 4 squared, this is divided by 12. So we have that value. So I will check the formula for fixed end moments for the different types of loadings. So we have that value equal to 160 over 3 kilonewton meter. So the fixed end moment on the left is expected to be negative in sign since it is counterclockwise. The fixed end moment on the right side is expected to be positive since it is clockwise. So since we have uniform loading of 40 kilonewtons, so we'll be having the same value of fixed end moments. It's just, we are just to adjust the sign. It depends if it is a support on the left or on the right. So we have the fixed end moment on the right, left side will be negative 160 over 3 kilonewton meter. If it is on the left, then we have the fixed end moment is equal to positive 160 over 3 kilonewton meter if that support is on the right. Alright? So what is our main equation when it comes to this procedure, the slope deflection method? The main equation is we have the moment of the near point is equal to twice of EI divided by length. This is multiplied by twice of the near point, or the rotation of the near point, or this is the rotation of the support, plus the rotation of the far point minus 3 times the chord rotation plus the fixed end moment of the near point. So let us have first member AB. So let's say, okay, the moment for span AB is equal to, your near point is A, your far point is point B. So this is twice of EI, the span is 4 meters, multiplied by twice of rotation at A, this is your first letter of the subscript. Okay, plus the rotation at B, this is minus 3 times 0. Again, psi is equal to 0 if you don't have support settlements. So again, for this case, no support settlements. Then minus, this is the fixed end moment on the left side, AB. So we have negative fixed end moment, that is negative 160 over 3. So we simplify, this is the moment for member AB is equal to, so 2 times 2 is 4. We have this is now EI theta A, okay, plus we have EI theta sub B, this is divided by 2, this is 2 over 4. Then 0 minus 160 over 3. But if you are to observe, what is the summation moment about point A? What is the summation moment at A? This is hinge support that is equal to 0. So let this be equal to 0. So which means we'll be having our first equation. This is EI, the rotation at A, plus EI, the rotation at B. This is divided by 2 minus, or I'll be transposing this value, equal to positive 160 over 3. So this will be our equation number 1. Alright, considering span AB. Okay, so let us consider the next span. That will be the same as span BA. So the same span, all we have to do is alternate the letters. Alright, so span BA, let us establish the equation. This is the moment BA is equal to twice of EI over L multiplied by twice. What is our near point? That is point B. Alright, twice theta sub B plus theta sub A minus 3 times the psi. 3 times psi. Okay, minus 3 times psi plus the fixed end moment. Fixed end moment BA. So we'll be having the equivalent of, this will be the equivalent of moment BA is equal to twice of EI, the same span, 4 meters, divided by 4. This is multiplied by 2 theta sub B plus theta sub A. This is minus 3 times 0. Take note, we are now considering span BA. That will be a positive fixed end moment. This is positive 160 divided by 3. So we simplify, this is the moment at BA is equal to, is the same as EI theta sub B plus EI theta sub A minus 0 plus 160 divided by 3. So, yes, right? I think EI, 2EI over 4, this is EI theta of A divided by 2. So this will be the equivalent of moment of BA. Now we may proceed to the next span. Take note that point B is connected to 2 spans. Alright, so point B connected to 2 spans, BA and BC. We need to consider span BC. So for span BC, this will be the moment for span BC is equal to twice of EI divided by the length. This is multiplied by twice of the same as theta B, your near point, plus theta C, your far point, minus 3 times psi ay plus your fixed end moment member BC. Okay, so we have the moment for member BC is now equal to, this is 2EI, this is divided by 4, multiplied by twice of theta sub B plus theta sub C, again minus 3 times 0, then how about this one? Plus the fixed end moment for member BC. So take note, this is a left support, so it is expected to be negative. Negative 160 over 3. Okay, so we have now the equivalent of moment BC is equal to, we have EI theta sub B plus, we have EI theta sub C over 2, then minus 160 over 3. Okay, so we have for joint B, if we are to consider the moments per span, let's say this is the moment for member AB, member BA, let us assume that it is counterclockwise, and for the span BC, this is the moment BC assumed to be clockwise. Basically, they are acting in the opposite direction. So we'll be having the summation of moment at B should be equal to 0. So which means that is the moment BA plus the moment BC should be equal to 0. So the summation of moments about that point or about this joint B should be equal to 0. We have to consider the moment for span BA and span BC. So it's equivalent of moment for BA. We have we have EI theta sub B plus we have EI theta sub A, this is divided by 2 plus 160 over 3. So this is the equivalent of moment BA plus, what is the equivalent of moment BC? This is EI theta sub B, I plus EI, this is theta sub C divided by 2 minus 160 over 3 is equal to 0. So when we eliminate 160 over 3, so we will be having the equivalent of 2EI theta sub B, okay, plus EI theta sub A divided by 2 plus EI theta sub C over 2 is equal to 0. So multiplying both sides of the equation by 2, we'll be having, this put first the theta sub A. This is now EI theta sub A plus 4EI theta sub B plus we have EI theta sub C is now equal to 0. So let this be our, this will be our equation number 2. And then we have to consider the last span, that is span CB. Okay, so for our last span, we have span CB. That is, we have the moment for span CB is equal to twice of EI is divided by the length divided by twice. Your near point is point C plus theta sub B minus 3 times psi plus the fixed end moment for member CB. Okay, so we have the moment for member CB is equal to twice of EI. The length is 4 meters divided by twice theta C plus theta sub B minus 3 times 0, then plus. Take note, this is a right support when if you are to convert it to a fixed support. So it's expected to be a positive clockwise moment. That is plus 160 over 3. So we have the equivalent of a moment CB is equal to, so 2 over 4 times 2 is the same as EI theta C plus EI theta sub B, that is 2 over 4 divided by 2. Then plus 160 over 3. So in order to compute for the moment at C, since that is our summation moment about C, it should be equal to 0. And other than that, it is a ruler support. So it is expected to be 0. So we have the third equation. This is now EI theta sub B divided by 2. I plus EI theta C is equal to transpose. This is negative 160 over 3. So let this be our equation. Okay, equation number 3. So let us recall the two other equations earlier to compute for these unknowns. Okay, so let's have our equation. So equation 1, EI theta A plus EI theta B over 2 is equal to 160 over 3. We have second equation. This is EI theta A plus 4 times EI theta sub B plus EI theta sub C equal to 0. And our third equation, EI theta sub B plus over 2 plus EI theta sub C is equal to negative 160 over 3. We also included the previous equations, the moment BA and the moment BC, since we are computing for moment at B. So let us compute for the equivalence of our unknowns. Our unknowns will be EI theta sub A, we have EI theta sub B, and EI theta sub C. So 3 equations, 3 unknowns. So the equivalent of EI theta A is equal to 160 over 3. Alright, so we have theta B is 0. Then EI theta C is equal to negative 160 over 3. Alright, so since we are computing for the moment at B, you need to consider these two spans, moment BA and moment BC. So by substitution, so we have, this is EI theta sub B is, we have this as 0, EI theta A, that is 160 over 3 divided by 2 plus 160 over 3. So we'll just remove this one. So what will be the moment? BA. That is equal to positive 80 kilonewton meter. While for the other moment, we have, this is a moment BC is equal to, we have EI theta sub B I plus, we have EI theta sub C over 2. This is minus 160 over 3. Again, EI theta sub B is 0. So this is EI theta sub C, this is negative 160 over 3, that is divided by 2 minus 160 over 3. So this will be the equivalent for moment BC. Alright, so it's the same as negative 80 kilonewton meter. As you can see, numerically equal but opposite in sign. If we are to draw the equivalent free body diagram of that support, support B, which is a roller support, supposedly we have a negative bending moment. Okay, this is for the span AB. Okay, so we are able to compute for a positive 80 kilonewton meter. So that is, we have the 80 kilonewton meter. This is the moment for span BA. Then we have on the other side, so we have to compute a negative moment. This is negative 80 kilonewton meter. And this is the moment BC equal to negative 80 kilonewton meter. But actually we have for equilibrium, so supposedly we have here a negative 80 kilonewton meter, okay, against the BA, and we have a clockwise moment of 80, okay, so against BC, which is the negative 80 kilonewton meter for equilibrium. Okay, so therefore, our actual moment at joint BC, that is a negative bending moment. The actual moment is negative 80 kilonewton meter. That is a negative bending moment since the bend opens downward. What is our example for slope deflection method?